Second day, and we are now starting the third day with the second lecture of Professor Francesco Ginelli. And please, the floor is yours, Ginelli.
Okay, so if you remember Monday, 2 days ago, we introduced the subject and we started to analyze collective motion, focusing on what happens near the transition between disordered particles and particles who flock in the same direction, okay? And we arrive with a little bit of hand waving, which I will try to make more precise tomorrow, to this picture where there is, if you remember, a transition, which is controlled by the main parameters, which are the total density or the degree of noise you put on your system. And, okay, here I'm putting the temperature instead of the noise, but just a nomenclature. These are out of equilibrium systems. And basically, you move from a gaseous-like disordered region to a liquid-like polar region. And I claim that there are all the signature, or there's some kind of mixture of the signature of the liquid gas transition and the disorder, the magnetization transition, okay? But in a sense, the fact that you have phase separation masks the latter. So you have a transition which is not a critical transition in the sense of critical phenomena, even if you look at sufficiently small system, you may find all the signature of a critical second-order phase transition, okay? Which just disappear if you get to larger and larger system. That's more or less where we got for. Now, what I'm going to do is concentrate. I get deeper in this polar liquid phase, and I check and I try to explain you which are the properties of collective motion when it is well-formed, okay? So when it's not near the transition to getting disordered, but where fluctuation, I mean noise, at the individual level is small enough to allow for a well-developed flock. Okay, this phase is typically called Tonnerre-2 phase, since it's Tonnerre-2 in a seminal paper which started to study it theoretically. And is this one? Okay, now our phase diagram. Okay, what I try to convince you is that this phase has some very interesting properties, which, okay, are essentially a consequence of the spontaneous symmetry breaking and of the motility of the non-equilibrium nature of your particles, okay? Now, even without going to non-equilibrium system, it has been long known that if you break spontaneously a continuous symmetry, you obtain an entire phase, an entire ordered phase, which has some very peculiar properties, okay? And this is due, if you want, tomorrow we will try to get deeper in why this happens, but the essence of the idea is the following. Okay, Julia already introduced to you yesterday the concept of a free energy potential. In equilibrium, this is some kind of complete treatment. Here, we don't have, here out of equilibrium, we don't have formally a free energy, but our system essentially responds in the alignment part to the same kind of forces. So you can think that your forces are derived by this kind of potential, okay? Which is colloquially known as Mexican antipotential. Okay, and in general, this is the Landau theory for the Ising model predicts or assumes that if you lower the temperature from the disordered to the ordered phase, your potential changes in this way. Okay, so at high T, which in our language will be high noise, the minimum of the potential is here, so there is nothing much you can do. And your state, if you expose your state to small fluctuations, small perturbation, all it can do is oscillates around a single minimum which has zero magnetization, okay? Sorry, let me write. Magnetization, this is zero, and this is your potential. Okay, this is the picture of the Ising. But when you lower the temperature or you lower the noise, your potential changes. And the zero magnetization state becomes unstable to small fluctuations. And so you spontaneously will break the symmetry. The symmetry in the case of the Ising model is a discrete symmetry, Z2, between positive and negative magnetization. Since in the spin model, in the Ising model, remember, spins are either pointing up or down, either plus or minus. They only have a binary choice. And so you spontaneously will fall either on this side or on this side of your potential. When you're here, you have a non-zero magnetization. So your system got a magnetization, but you're still constrained, since now you live again at the bottom of the well, and so small perturbations are going to be reabsorbed, okay, since there is a confining potential around you. This is the standard picture of the Ising physics, and it only leaves a narrow space for critical behavior when, okay, the kind of potential is like this, where now phi, think of phi as a magnetization in my graph, where this is a scalar. So there is only a very narrow range for a critical behavior, which is when this alpha parameter is zero, okay? And this is the critical temperature, okay? At the critical temperature, you see your quadratic confinement disappears, gets zero, and you have an intermediate region, state between this situation and this situation, okay? But it's just a very, very single point. An isolated point is the critical point of the temperature, where you're not confined in an harmonic potential. Now, when you go to a system which is not breaking at Z2 symmetry, but now you allow more freedom to your spins, to your arrows, which is the case of birds. Birds, of course, are not limited to flying north or south. They can go everywhere, okay? So for birds and in our V-check model, which is intended to capture the fundamental physics of birds to a certain level, your arrows can point in every direction, okay? So if you limit it to two-dimensional systems, so if you have, I don't know, critters crawling on a two-dimension on a flat surface, or, but for simplicity, nothing changes in 3D in this picture, but this can be a picture on your blackboard. Now, your order parameter is not anymore a scalar, but is a vector, okay? It's a vector which can point everywhere in the plane, since it's the average orientation of all of these arrows, okay? And now, how is done your potential? Your potential in the ordered phase is going to be like this, in the disordered phase like this, but it acquires an extra direction, which is here, okay? So this parabola becomes a paraboloid, since there is a direction coming out the blackboard, and so you should imagine a paraboloid. And this double well potential becomes a Mexican hat. Okay, now what is changing? Of course, if you take a transversal section of this potential, you're still getting the double well potential of the Ising theory. So you say, okay, I'm trapped. But mind, now the trapping is only in the radial direction. You see, if you take a section, you get this picture here. But there is another possibility. You can have perturbation which are not acting in the radial way, but they are acting transversally in this direction, okay? And here, well, here you have a valley. And how much energy does it cost to move around this valley, which is flat? 0. So it's free, okay? It's a free lunch. So this tells you that fluctuations which are transversal to the modulo of your magnetization are not damped in any way. Okay, they are free. And this gives much more freedom to your system, and indeed makes it much similar to what happens in the Ising model exactly at these t equal tc points for many aspects. Okay? Tomorrow we will try to get a little bit deeper than these, okay? But what happens is that these transversal fluctuations are free, are not damped, so they represent massless modes, and these are known as Nambu-Goldstone modes, basically, and they appear every time you have a spontaneous symmetry breaking of a continuous symmetry, okay? I hope I convinced that it cannot happen for a Z2 or for any discrete symmetry. Okay. The consequence of this, which for the moment I ask you to take for granted, is that you have a diverging correlation length, pretty much as it happens, as I told you, at the critical point of a standard discrete symmetry breaking. Okay. So it means that this characteristic length scale of your system, Xi, diverges. But it's not doing just at the transition point. Okay? It's doing in the entire ordered phase. This situation here represents not the system near the onset of collective motion, but it represents the system deep in the collective motion phase. It means represent the system in a situation in which all your particles, all your birds, all your crawlers or your cells are moving more or less in the same direction. You may have very, very little fluctuations. Of course, these, if you have a typical direction of motion theta, theta 0, each particle may have different fluctuations. But even if these things are very small, if the delta theta is very small, so everyone really goes almost in the same direction. So you have, this implies that you have a very high order parameter. Okay, remember, we define the order parameter as the average of all the individual velocities. Okay, so these things in modulo is very, very close to being 1, or the average velocity, okay? Let's call this S. This is just the orientation. Even when this thing is very close to be 1, this mechanism is acting, okay? So you're very, very far away from a transition point, and you have a diverging length scale, a diverging correlation length. Okay. Remember, I would like to point it out again, that even this is even stranger situation, since we discovered that the continuous ordering transition at our transition point in the case of collective motion, for large enough system, is masked by this phase coexistent region. So what this tells you that there is no diverging length scale at the transition point, if you consider a large enough system, but there is as soon as you get deeper. So here you have a diverging length scale, here you don't have it, okay? It's even a stranger situation from this point of view, but it is how it is. Okay. Now, you have already been likely exposed to correlation function and their Fourier space transformation, the structure factor, by Rodrigo. And these are going to be the honored guests of this lecture, I think. So basically, the fact that you have a divergent correlation length translates in the fact that your correlation functions are going to be power law, or, as people like to say, scale-free. Scale-free since any power law behavior lacks an inherent scale. What happens is that this scale here was sent to infinity, so we don't have, in an infinite system at least, we don't have anymore a scale. Okay, so what we are interested is correlation between fluctuations, of course. So the idea of correlation is really very simple. Let me use this. I have my flock with a lot of errors. Okay, and I wonder, okay, but if I take an error here, okay, and then I take an error here, and these two things are separated by a certain distance r. Okay, how similar are my velocities? Okay, now when you are in the order of phase, if you ask how similar are your velocities, the answer is a little bit trivial. Since everyone is going in the same direction, what is going to happen? That the velocities are very similar. Nothing else may happen. But now you can be a little bit more refined and say, okay, I know you're ordered. But now, tell me how are the fluctuation of the velocity correlated, okay? So don't look, okay, here I'm doing for a general field, since we will also do this for the density field. But the idea is don't look at the velocity, or you can also think of the local density is the same. So don't look at the field, which you know has more or less the same value everywhere in the ordered phase, but look at the fluctuation with respect to this same value, to this average value, okay? So now you're looking not at the velocity itself, but at the small fluctuation with respect to the mean velocity. Okay? Now, so these things technically are called connected correlation function for reason which came out of basically field theory jargon. But if you don't like, I mean, you can say connected correlation function when you speak with high energy people, so they understand you, or you can say correlation between fluctuations, so that it is what they are. Okay, and you've seen that the real space, so you can write like this. You check your field at position x plus r, and then the position x, and then you do an ensemble average over all the possible realization. By the way, if you assume that your system, for instance, is translational invariant, this is equivalent to make an average over all the x in your system. And you can go to Fourier space, so you can do a Fourier transform. And this is called, in Fourier space, the structure factor, okay? And by the Wiener-Khinchin theorem, which I think Rodrigo mentioned, this is equivalent to the average of the square of the Fourier transform of the field itself, okay? Which is, by the way you should use if you want to compute this object, okay? Since, remember, small detour. Have you mentioned this, that is easier to compute in Fourier space? Okay, sorry, I missed that. Okay, sorry, you have heard. Okay, no, I'm saying again, so if you want to compute this kind of two-point correlation, you should again do numerically loop over all your points in this, or your couple in the systems, which is an n-square operation, while this route here is faster, since just requires to do Fourier transform, which in the fast Fourier transform algorithm are much, much faster. Okay, that's in a nutshell. Okay, by the way, here I'm totally omitting the time dependence of my fields, or my quantities, or my velocity, or my local densities, etc. So these are formally equal time correlation function. Of course, you can also go and have a look at these kind of things at 2 different times. Okay? We will come to this later, but for the moment, stay equal time. Of course, if you look at correlation between velocities, local density at different times, this gives you extra information about the dynamics of your systems. Okay? Wrong direction. Okay, now, as I told you, since we have a diverging length scale, a diverging correlation length, the consequence is our correlation function are going to be power laws, okay? Here, which means that at large distance, they decay as a power law. So R to some minus, to some negative exponents, okay? Minus gamma, where gamma is typically a positive exponent, okay? This also implies that typically if you Fourier transform and you do a little bit of, let's say, dimension analysis, this is also has a strong implication on your structure factor. Now, your structure factor, since essentially wave numbers Q are the inverse of, roughly speaking, are the inverse of the distance. So this means that now the power law decay in large distance becomes a divergence in your structure factor at very small Qs, okay? As small wave numbers. That should be a gamma, there is a mistake. Okay. I mean, the idea is pretty simple. Then I am doing, yes, I'm doing the opposite way. Oh, this is an R, of course. Okay, so this is the object I've written up there. I'm using a minus as a convention. Okay, so this is at large distances, this goes like R to the minus gamma, this thing here. Okay, and now you can transform these. You can introduce now, if I drop the error of symbol, I'm taking the modulo of my wave numbers. Same thing with R. Okay, so this is minus I, the 2 modulo times the cosine of the angle between the wave number I'm looking and the separation I'm looking at. Okay, so I'm looking, I don't know, at the separation R here, and I'm interested into a wave number which has this orientation, and this is theta, of course. Okay, and here I can go in polar coordinates. So here I have an integral over the solid angle, and here I have an integral, and there's no fit in the R, and here R to the d minus 1, R to the minus gamma. Okay. So you see immediately that now, if you, let's say, introduce a new variable, R, which is R small r times q, if you introduce big R, you can change your integral, and here you will have 1 over q to the d minus gamma. Basically, you transform all the R in this way, and you get powers of d, okay? And here you have an integral in the omega. Here you have an integral in the large R. Here you will have R to the d minus 1 minus gamma, large R, exponential I R cos theta, okay? So basically, nothing here inside depends anymore on the modulo of Q. Okay, you have a dependence still which gets out of theta, but now, if for simplicity, now we will see later a slightly more complicated case, but if for simplicity we assume our system to be isotropic in all spatial direction, which means that you assume that the correlation at a distance r in this direction is equal to the correlation at a distance r, the same distance in that direction, so everything is invariant, which is strictly not as to be the case for flux, but for simplicity now, take the argument for the isotropy, so all of these things doesn't depend anymore, cannot depend anymore on the orientation, and so you get out this result, okay? Oh, what happened?
I tried to put your computer without Zoom because the internet.
Ah, okay, sorry. Let's see how it works. Yeah, sure. Okay, so far the main message is when you break a continuous symmetry, you will have correlation function between fluctuations and the corresponding structure factor, which has a power law behavior. In real space, correlation function falls very slowly, falls with a power law. And in the corresponding Fourier space, your structure factor diverges at small q's, again, as a power law. Okay, this is the main message. I can try to use my personal.
I mean, but even here, we just plug this.
Yes.
We're using VGA here.
Yes.
Work straight away, or you need to press something inside here.
No, let me just try to. Okay, no, but if I can try to use my okay, no. Oh, this is strange, but we can try to use my personal.
I mean, regardless of the internet, the question now is about going from here to there.
Okay, but this is okay. So also this one. Okay, but we can try to use my internet.
No, but down.
Also on this one. Ah, okay. So this is not going. Since this is wireless, how it's going?
I can try connect to the Zoom again.
Okay.
Maybe it's not working, the VGA here. Why is it not working?
Your screen is mirror or?
Yeah, no.
Exactly.
It normally works. I don't understand what is going on.
HDMI as well, adapter.
HDMI don't work with the Mac.
Okay, now in principle, it should be. Okay. Look, so can this one be connected?
It's not connected. See, I tried to.
No. But I mean, can this one be connected to the?
Yeah.
Since I can just transfer my presentation.
Yeah.
Is there an email I can? Or if you have a pen drive, yes. Sorry, guys. Technical. Oh, if you have any questions so far, that's the right moment. Yes. Microphone.
You said that for flocking, the correlations are not isotropic, right? So
Yeah.
I assume you have some component that's parallel to the direction where the
Yes,
flocking
exactly,
is.
exactly,
Yeah,
exactly.
perpendicular component.
Exactly. So the law is, and this is a very good question, and in all it followed, since we spontaneously broke a continuous symmetry, it means that our flock selected a direction where it's going. Okay. By the way, in any finite system, this direction is not fixed; it's diffused around due to fluctuation. But at a certain instant of time, there is a well-defined direction. This is the broken symmetry direction. This leaves d minus 1 directions. In 2 dimension is 1, trivially, or if you have 3 dimension, more than 1, 2. And these directions in principle are different. Okay? And they are different for the argument I tried to give you. Well, intuitively, they're different for the argument I tried to give you on Monday, that transversal perturbation. So if this is the mean direction, you have longitudinal perturbation and transversal perturbation. And these behave like the sine of a small fluctuation, and these behave like 1 minus the cosine of a small fluctuation, delta. So this is going to be delta square, and this is going to be delta. So you realize intuitively that there is a difference. So all the treatment historically has been done with this anisotropy in mind between the longitudinal and transversal. Now, the funny thing is that in recent years, we realized, first by analyzing carefully numerically these model systems, and then there is a very, very recent result which has just been published by Sonon and Chatet, and also other groups, that this anisotropy on very large length scale disappears.
What does it mean, very large length scale?
That your anisotropy exponent, anisotropy scaling exponent is strictly 1. Okay? And, okay. But in principle, the things can be different. So typically, the treatment is done distinguishing between these 2 directions.
And do you also get different exponents for,
Yes,
for the
yes,
structure
yes,
factor,
yes.
right? Yeah.
Yes, okay, I anticipate, but
Yeah, has it.
for instance, what you get, okay, let me, this was on the next slide, I think, or nearby, but so it means that if you look, for instance, at the correlation function between velocities with a separation r, now you have 2 possibilities. This can be if the dominating distance is perpendicular with respect to the direction of motion, this has a certain exponent, which traditionally is called 2 chi, and the behavior is 2 chi. This is basically, here chi is negative. Don't ask me why historically went out this way, since it's a little bit confused the fact that it's negative. But, so this is decaying, and chi is a scaling exponent associated with how the fields change under rescaling. It's what is called the roughness exponent in the jargon of statistical physics. But, and this is for R perp dominating R parallel. And then you have, sorry, in the other case, you have R perp is decaying with 2 chi over psi, and psi is an anisotropy exponent. Okay? This is R perp, much less than R parallel. Okay? And then this is, okay, this is a good approximation. Now, since you have this anisotropy running out here, you also should include in your limiting condition. So this is not R perp, but is R perp to this anisotropy exponent here. And by the way, if you want to include, sorry? Yeah, sorry.
Right, well, when you finish this bit.
No, you can also include if you're going to spatio-temporal correlation, you also want to include the time. You have essentially a similar anisotropy with respect to time, okay? So you may distinguish when you look at spatio-temporal correlation function when your separation is dominated by time or by space, and you have a similar correction. We will see later, which include a further exponent which tells you how much space is different from time in your spatio-temporal picture.
Yeah, sorry. Maybe I'm missing something totally basic, but you're using equilibrium statistical physics to do this. You're using the language of equilibrium statistics.
I'm using a language of equilibrium.
Why can you do that for a non-equilibrium system?
I mean, this is what essentially, but in a sense, this is what comes out if you do an RG, a dynamical RG analysis, which is a non-equilibrium thing, of hydrodynamic equations, okay?
Yep.
At this level, I'm giving it for granted. I will try, today I want to explore the consequences of this. It's a more phenomenological lecture. Tomorrow, I'm trying, to the best that I can, since the original work is pretty complicated, to explain how the hydrodynamic theory and the dynamical RG gives you this kind of results.
Okay, thanks.
That's at this level, you should take it for granted, but in a certain sense, the claim is that what you get out of the non-equilibrium situation is an analogous of what you get at equilibrium. Of course, you have different scaling exponents, so these numbers are going to be different. Okay. So anyhow, as I told you, it will turn out that probably if numerical simulation and recent developments are correct, there is still a little bit of debate on that, so I don't want to weigh down, but probably these things is equal to 1. So on large scales, this spatial anisotropy is going away. Okay, so this is the first claim I'm doing. As Julia correctly pointed, I'm not demonstrating this for the moment, apart with this analogy. Okay, now you may wonder, is this true? And these things emerged clearly in this beautiful paper by the Roman group, the COBS lab of Irene Giardina and Andrea Cavagna, 15 years ago almost. So they've been the first to be able to reconstruct, to measure in a quantitative way starling flocks, flocks in general, birds' flocks. They chose starling flocks. In Rome is along the migratory direction of the starlings between North Europe and Africa and back. And when they're in Rome, they like to rest in Rome. And so they stay there for a while. And of course, this measure is not being during a migration, which you may argue is not. In a migration, you don't choose spontaneously where to go. Either you go north or you go south. But it's been done during a very peculiar behavior these birds have, since these birds like to roost in a few areas in Rome. Ethologists tell us this is an area where there are trees and they are warm enough. So one is near the train station and the other is in a residential area in another place. And they roost there. In the morning, they divide in groups of some thousands of individuals. They go around I suppose, to eat and do other stuff. Difficult to know. In the evening, they came back, and they do a lot of evolution in the sky for half an hour, 1 hour. This is where the movie, which I was trying to show you on Monday, was recorded. And then, after all this time, they go down to sleep on the trees, okay? And so this has been recorded intensively during this kind of evolutions and during this kind of behavior. This has been done placing cameras on the rooftop of buildings in Rome. I've been up there to see the thing, and they used triangulation. So with the triangulation, they had 3 synchronized cameras. They were able to reconstruct positions and to a certain extent, to a very good extent, trajectories of these birds in these three-dimensional flocks, up to a few thousand of individuals. There are larger flocks, I think, more than 10,000 of individuals, but these are more difficult for obvious reason to process experimentally, so I don't think they have anything larger than 10,000 or even 5,000, okay? But this is the kind of system they've got. And they've done a sequence of papers, this is one of them, where they measure the velocities of birds in these flocks, okay? And when you have the velocity, you can do the correlation function, as I told you. They did them at the individual level. So these are the velocities as they reconstructed. It's a single snapshot, of course. Then they did it for several seconds and for several different flocks. And these are the velocity fluctuations, okay? This object here. Here, S is for the individual velocity reduced to a unitary vector. So they did just the heading. And these are the fluctuation with respect to the mean motion. So this is the thing, as I told you, we want to correlate. They computed the correlation function at the microscopic level. That's it. And they go and looked at this correlation function. Okay, before I show you the result, I have to add a little piece of information, which again came from equilibrium stat phys, is that what I told you about the lack of a scale is true in the thermodynamic limit, okay? So, I mean, I told you there is a scale which diverges. Perfectly true, but as I told you, they are measuring flocks of a few thousand of birds, and from that picture, you see that the flock is finite. It has a certain total size, which is L, okay? So obviously, your correlation function cannot be larger than L. And you need to take into account the fact that fluctuation, when you compute the fluctuation of the velocity in a finite system, the sum of all the fluctuations has to be 0, obviously. So if you have, if you have that delta is I and you sum for all the birds in your system, this has to be 0, okay? Otherwise, you will be changing the mean, okay? So since this fluctuation has to be 0, okay, or in a continuous thin language, if you integrate over your entire volume, L of D, let's say you have a velocity field fluctuation, this has to be 0, you can check that this implies that also the integral of your correlation function over the separation R over your entire system, sorry, over R, this is not the volume, sorry. Well, okay, let's take it like this. Let's take it full. Also, this has to be 0, okay? And this implies also that if your correlation function is isotropic, if you just integrate over the modulo, this is going to be 0. Okay. What I'm trying to tell you is that in a finite system, you don't have a power law decay. Okay? Since in this case, the integral would be non-zero. Your power law decay gets a correction, okay, due to finite size, and is something which does like this. Okay? And you need to have it 0. Okay? Since in this way, the integral up to the system size can be 0. Okay? So let me see if I wrote it. No, I haven't wrote it. Great. So let me write it here. So in a finite system, what you expect is that your correlation function behave like this. And here you have a certain length scale RC, where G So when R is equal RC, GD1 is equal to 0, okay? GD1 is changing sign, and you can take this RC as actually a measure of a correlation length. This is the scale which is left in your system. Now, you may tell, okay, but so there is a scale, you're cheating. But this scale is nothing but is proportional to L, okay? This scale, RC or psi, call it, it will be L times a certain constant C. Okay, so this implies that when you send your sides to infinity in the thermodynamic limit, you recover a pure power law, okay? That's the thing. So the message is, if you're looking at correlation in a finite system, which is what you have to do if you're doing biology, you expect something like that. Okay, sorry. There I was using lambda, not... Okay, not R. Okay, so when you expect that kind of behavior, you expect a correlation function which decays, of course, with the separation up to a certain point, the 0. The 0 can be used to define a correlation length. But the interesting thing is that this characteristic length scale of your system is not intrinsic. Okay, if you would have a normal system without this power law behavior, lambda would be an intrinsic quantity regardless of the size of your system. Okay? Normally, correlation length in non-power law system decay exponentially. Okay? Like this, and this object is a characteristic length scale of your system. There, this is not a characteristic length scale, and the theory tells you it has to scale with the system size. So what they did was they went and looked at different flocks of different size. And they measure this kind of correlation function in many, many different flocks. They got this range, which is almost one decade, between 10 meters of diameter to almost 100 meters. And they measure this zero crossing of a correlation function. That's what they found. Okay, remember, this is biology, so this is astonishing. What is telling you this thing? It's telling you that the correlation length grows linearly with the system size, okay? So it tells you that, of course, you can say, at least up to the measurable extent of their experiments, that their systems are really scale-free, okay? That there is not a characteristic length scale which is independent of the global system size. Okay, now, when you see this result, there are two kinds of reaction. One is, thank you, there is a spontaneous symmetry breaking. We know this is going to happen. But the other is, this is somehow a very strong statement, since these are birds, these are not arrows, okay? So birds are very, very complicated beasts. They have an internal metabolism, they are vertebrates. I mean, biologists can tell you that there are an incredible amount of factors. Now, you are playing with little arrows, and you tell me that something that your little arrows does, also the bird does. This is somehow, to me, it's a striking demonstration of the power of universality, okay? And this is one of the things I was trying to convey to you on Monday, that if you just abstract, so what do you need to get this result? You basically need to say, I don't care what a bird is, okay? And biologists fall down from their chair. I really don't care. The only thing I care is that they break spontaneously a continuous symmetry. They do this, they cannot escape these correlations, okay? No way they can, well. But if you don't add some extra dramatic ingredients, they cannot escape this. They have to do this, okay? And this is what was rather strong. Of course, I think if you read the paper, I mean, Irene and Andrea know it perfectly, but wrote it, I think, in a slightly convoluted way, so that biologists didn't really got this kind of message. So an intentional consequence of this paper is that for a while, a lot of people tried to do flocking model from the biology community. I think that they got the largest fraction of people, this paper to refer, but I also got some, where people were writing very convoluted flocking models with a lot of more ingredients. And then they were saying, look, in this flocking model, I have scale-free correlation, so it should be correct. It should be more correct than, and of course I was telling you, this doesn't telling you anything. I mean, all flocking models should have this. Then if you want to go deeper, if you're a biologist, you're interested in more fine details, you're most welcome to try, and you're probably better qualified than me to do this, but this is not a proof that your model is particularly good. This is just a proof that your model is not blatantly totally wrong, okay? That's the message. But this is, I think, one of the order zero statement on why this kind of analysis based on minimal model is important, okay? So the statement I'm giving you are not statements about the specific Vichek model, are a statement about a universality class, which is called the Vichek or Tonerant-2 universality class, but which goes far beyond little models with little errors, okay? Exactly like the easy model goes far beyond little errors. Okay, now, there is already an interesting fact here that if you try to go deeper, and you try, as I told you, the way your correlation function behaves should be this one. So you should have this decay exponent here, okay? One thing I forgot to tell you. I told you, in principle, we know that there is anisotropy in these systems. Now, in experiment, measuring correlation function, distinguishing between the longitudinal and the transversal direction, is extremely difficult. For a number of technical reasons, not last the fact that finite system, as I told you, change in time the direction of flight. The total direction due to fluctuation diffuses. So it's extremely difficult to distinguish between the two. In all the experiments I know, I mean, then I will later show in another experiment which I did, you take isotropic averages. In a sense, you are averaging over the behavior in different directions, which gives you a more robust statistics, and of course, delete a little bit of information on the anisotropy, okay? So this has been done doing averages in all the direction. Okay, and sorry, then I came. No, okay, that's a good point. You had?
I would like to know if it does a negative correlation function has any physical meaning?
Anything?
Any physical meaning? A negative correlation function?
As I told you, it has to be. You can see it here. Since whatever. The sum over all the fluctuation should be 0. It means that if you look at the fluctuation, they cannot point all in the same direction. They have to cancel out. And this is what you see. I mean, these arrows, as I told you, these are the full velocity. They all point more or less in the same direction. If you take an average, you're getting the total magnetization of the flock, which is very close to B1. If you go here, the sum over all these errors has to cancel out by definition, since they are just fluctuation. And so this part of the flock is anti-correlated with this part of the flock. It's just a realization of this fact. Okay, two observations. First of all, I already told you, this has nothing to do with an ordered disorder critical point. We are in extremely ordered regime. If you measure the order parameter, the scalar order parameter, which I wrote somewhere, this one, in this kind of flux is around 0.95. So they are really, really ordered. They really fly in the same direction. Second observation is that even if we have this qualitative agreement with scale-free correlation, the exponent you get, this gamma exponent here, is in this experiment is almost 0. I would say that it's so small that you cannot distinguish from being logarithmic decay or 0. And this is, I wanted to talk about, I don't know if I will have the time on Friday since there is a lot of material I want to cover. But this is, of course, the proof that there is something more, since this almost 0 exponent you cannot extract either from equilibrium theories or from this hydrodynamic theory we're going to talk about next. This is a proof that there is something more. Now, actually, for this, we have an explanation. I can just give you the hand-waving explanation. And the hand-waving explanation is that you get this kind of effective near-zero scaling exponent, which means that flocks are really strongly correlated. They are as strongly correlated as they can. Since, I mean, if you have a system in which you have continuously dynamically changing perturbations, so you don't consider, either you don't consider an isolated system. Think of the movie I show you where there was a predator attacking the flock. The predator was circling the flock, and obviously you could see the starlings react with some kind of avoidance behavior. I mean, I like to call it terror when I don't know if, but they were obviously very afraid. They were constantly changing speed. And even if you look at isolated flocks, you realize that they turn a lot, since, of course, there is more than just flying together. Typically, they are doing this evolution around a roosting site. So it's not just that they go constantly and they just slowly and diffusively change their direction. Typically, it's probably when they are too far away, they turn, or they just turn since they have fun in doing that. Ethologists, but you see a lot of changing of direction in your flocks. And this could be incorporated, for instance, in your Witcher model, saying that sometimes some arrows change direction, start a change of direction with some kind of extra behavioral changes. You can show in simplified model that all of this kind of behavior, if it happens on the right time scale, can affect the effective exponent you measure, gamma, okay? So there is a perturbation theory which shows this, and of course, it's just a possible explanation, but just to tell you that when you go and look at biological system, or at least the approach I recommend, or the approach that I like, is to proceed one layer at a time, okay? So you say, okay, the most fundamental thing is the symmetry breaking, some consequences. Some things are okay with very simple model with symmetry breaking. Now there is some extra phenomena which we don't really understand, and of course it requires some kind of further dressing up of your model and so on and so forth. And in my opinion, this is a way to proceed, or at least the way in which physicists can be useful. Okay. Any questions?
I have a question about universality in general.
Okay.
Yeah. So you showed these measurements, one beautiful set of measurements
Yes.
that support this universal behavior. You don't care about what the bird is. And how robust is this? Do you know of other measurements that kind of seem to fall into the same universality class, so to speak?
How robust is with respect to, sorry?
To the kind of universal behavior that you expect from these measurements. You have other measurements for other flocking systems that fall into the same kind of universal behavior?
I mean, yes, I have one which I will show you later. I will have one with migration of cells, which has this universal behavior, and also the exponents are in a decent agreement with the theory, so there is not this perturbation effect. Of course, it's more controlled. It's something you're doing in a lab on a plate, and not in the sky. So we have at least another set of measures, I would say. I don't think there is any precise measure in fish. are there? You have? Okay. And? Sorry? Ah, okay, okay, good. You have to, okay, thank you. When will been done? Okay, oh, I miss, okay, okay.
What? Yes.
Yeah, yeah, okay, okay, oh, sorry, sorry, I totally missed it. I really want to see it.
And someone is trying with locust now.
Yeah, yeah, this I know, okay,
Yes.
this I know. But, okay, no, I'm really interested. Yeah, but I mean, I don't know how you did it. There was this long-standing idea, I think Ramaswamy mentioned to me more than 10 years ago, go on fisheries in the sea, do some sonar imaging of huge banks of fishes, and that you can basically measure the Fourier spectrum of the thing. But okay, that's very nice. Okay. Okay. This is more or less already mentioned. So this is just telling you the kind of corrections you get when you have a finite length scale. The real space is this one, and if you go to Fourier space, it translates in this kind of Lorentz, I mean, on finite mass correction in the denominator, which you see, if you have this finite term here, when you send the wave number to 0, you kill the divergence. So instead of having a structure factor, which diverges, so this is a log scale. Instead of having a divergence like this, when you have a finite correlation length, you go to a finite plateau, okay? So you kill off the divergence. And this is the typical behavior in systems which are not at a critical point and which do not break a continuous symmetry. Okay. This is the non-anisotropy, but I will skip it since we lost a lot of time. Okay. Now, as I told you, my correlation function seems to depend on a set of numbers. These are called scaling exponent. I don't know why I wrote critical exponent, which is not correct. It's scaling. Sorry, it's EBIT. But since critical typically refers really to the critical point, this is not at the critical point. So scaling exponent is more correct, sorry. And they are associated to the rescaling of your theory. You have, in this system, you tend to have 3 exponents, which basically tells you if you do a change of scale in your system with a parameter b, okay, it tells you how time, space, and field should be rescaled to keep some kind of scaling invariance. And so you have a set of 3 different exponents. This psi exponent here tells you how transversal and longitudinal direction in space, transversal with respect to the direction of motion and longitudinal are related, as I told you. This is this spatial anisotropy. The Z1, it tells you about time, okay? How time and space are related. And then you have a chi, which tells you how fields have to change, or cosine fields have to change when you change the scale. Okay, so you have this kind of 3 exponents, more tomorrow, but they are some kind of a central object of the theory in the sense that you expect to be universal. So you as long as you respect the same set of symmetries and conservation law, you expect, basically from equilibrium statistical physics, this exponent to be always the same, okay? Of course, on very large time scales, where all the microscopic details are washed up. Okay, so one kind of challenge is to understand which is the true value of this exponent, which has been a long story, and is still, in a certain sense, open. Okay, this I already told you. This is the Fourier space version. Okay. Okay. This is basically, I told you by hand. Okay. Oh, yes. So just let me point out. Okay. That this behavior in the two direction, transversal and parallel to the direction of motion, is the Fourier equivalent of this behavior I wrote here. But like you can basically, with the kind of transformation I show you, you can basically go from one to the other. You have to be a little bit more careful since there is an anisotropy, but it's easy to do it. Okay. Okay, the structure factor you have already seen. So, okay, here is what Rodrigo showed you, that if you define a number density in this way, you can relate your Fourier transform of the fields also with individual, with the structure factor computed from individual particle position. And this is extremely useful if you're doing experiments again. Okay, and finally, as I told you, even if the behavior of this correlation function is rather complicated by the anisotropy, a good procedure is just to take isotropic averages and circumvent the problem, okay, by averaging over all possible direction. Okay, this is even, okay, another thing, which I forgot to tell you, sorry. Now, if you would be doing equilibrium physics of spin on a lattice, fixed on a lattice, all you matter about are spin-spin correlation function, okay? Spin is your only variable. Now, our system, on top of these spin dynamics, has particles which move. The fact that they move implies that also the local density changes. So you have seen the movies. You may have clumps of dense areas where you have a lot of particles and more depopulated areas. So also the density field is a relevant field. And the interesting thing of this system is since density is carried on by velocity, so particle moves in the direction of their spin point, all of these scale-free correlation of the velocity field carries on to the density field. Okay, so not only you have scale-free correlation in your velocity field, but you have also in the density field. And now, the form of this, the non-isotropic form of this density correlation in principle is even a little bit more complicated, but for the moment, ignore this complication and think that you have even 3 possible directions in principle, that you take isotropic averages. Okay, now, what I would like to do is going beyond the mere scale-free nature of the correlation function to explore a few consequences of this scale-free nature. There are a few which are rather famous. One, the fact that your fluctuation in your system are anomalous, okay? Fluctuation in the local number densities. Okay, so the idea is the following. Take your flocking system and find a small region inside your flocking system, measure the average density of particles, and then measure the fluctuation on this average density, okay? You can do a measure in time if you want. So you find the region, you count how many particles you have at a certain time, you wait a little bit, you count again, you wait a little bit, you count again, so you have a time series of local number of particles. You divide by the volume of your selected square, by surface in 2 dimensions, and you get a time series for the density, for the number density, for the number density fluctuations, okay? Or here, okay, here I'm expressing directed number of particles and fluctuations in the number of particles. The number of particles, of course, if your system is homogeneous, has to be the global density times the volume of your little cube, and then you want to measure the fluctuations. Okay, now, if you do in any decent behaving systems, due to the central limit theorem, this kind of things that you know that the fluctuations are going to scale as the average number of particles to the power 1/2, okay? So it's the square root of the average number of particles. But if you do in a flocking system, you find that there is a power law relation, but with an anomalous exponent which is larger than 1/2, okay? So you have larger fluctuations, okay? Well, larger, you have stronger fluctuations. One has to be a little bit careful since the point, the idea is that they are not simply wide fluctuations which are large in amplitude. They have a different scaling, and this different scaling is due not to the fact that there is a lot of local fluctuation, but that these fluctuations are correlated over a large distance, okay? I told you, you have your correlation function decay algebraically, so they decay very slowly. And so when you start to integrate them over larger and larger volumes, you get very, very slow, I mean, you get stronger fluctuations once you integrate them, okay? But this is the consequence of a slow decay. So you have a procedure, which is compute this kind of averages and fluctuation in larger and larger boxes, and you expect that it should give you this relation with an exponent which is larger than 1/2. Why is this the case? This is strictly connected to the fact that your structure factor is diverging a small wavelength. Okay? Now, you can try to do this calculation analytically, starting from the idea that you know how your structure factor behaves as Q goes to 0. Okay? So if you consider a box of size L, you can compute the average number of particles in your box by integrating over the density, but you know that is going to be this quantity here, of course. So the total number of particles times the fraction of the volumes. So the volume of your block divided the total volume. And you can compute also the fluctuation like this, okay? Inside your block A. Okay. This is limited to a portion of your system, so this quantity doesn't go to 0. It's a local fluctuations. Okay? Now you take the square of the fluctuations. Okay, so you take this object here, you square, and you take the average, and you obtain a correlation function between local density, okay, into different points, x and y, and you have to integrate over the volume you choose, the volume A. Okay, now integrating over volume A can be made by introducing the characteristic function. Okay, the characteristic function psi is a very simple object which tells you if x is in A, your characteristic function is 1, otherwise it's 0. Okay, it's just a trick. Done that, you can observe that this object, which is a correlation function of the distance between x and I, is the Fourier transform of your structure factor, which is this thing here. And this you can turn down in a Fourier transform of your correlation function, okay? By convolution. And what is your Fourier transforms of the characteristic function. Now, if you do the Fourier transform of the characteristic function, you find essentially this sinc function. You can try if you want. which is the sinc of x is sine of x divided by x. But here you have a factor L. This L here is the linear extension of your box. And if you have this kind of object and you wonder, which is the behavior of this kind of object as I send L to infinity? Okay, these things, as L grows, approaches a Dirac delta. So what I'm telling you is basically that once you arrive to this form, this object here tells you, okay, the only thing which really matters of a structure factor is the low wave number behavior, okay? And the low wave number behavior, so here you have the average number of the particles times this quantity here, and this is your delta n square. So you have that at the end, the ratio between your fluctuations, your square fluctuations, and the average number of particles is given by your structure factor behavior at low wave number. Okay, now, this is perfectly true always, not only for flux. Typically, as I told you, your structure factor, if you're not in a divergent correlation system, at a certain point, as Q goes to 0, goes to a constant value. Okay? So this tells you, that's easy. That's a constant. Typically, that's related to the compressibility in equilibrium statistical physics by a temperature and the density. And so it tells you, okay, the square fluctuations are of the same order of magnitude of the average, okay? So that if you do the square root of a square fluctuation, they go as the square root of the number of particles. But now this thing is not going to a constant. This thing is diverging, okay? It's diverging like Q to some exponent. Here I'm calling Greek Z, since this is how typically we call it in the toner and hydrodynamic theory. And this is actually limited by the small frequency cutoff, which is the box size. So you have basically that this ratio is equal to L to this exponent, and at this point is just algebra. Okay, you note that your average number of particles is proportional to the L to the power D, and so you can relate everything, and you obtain that your square fluctuation are equal to your average number to the 1, which is the normal behavior, plus this anomalous part, Z over the dimension, which comes from this divergence. Okay? Final result. 1/2 central limit ordinary behavior plus a correction, which depends on the scaling properties of this torrent 2 region. Okay, that's the prediction. Of course, I haven't told you so far what is this exponent, but the result from numerical simulation in both 2 and 3 dimensions is very close to be, for the total alpha, 0.8. So this correction is 60% of the central limit theorem value. Yes?
But previously you said that in this flocking system you have some anisotropy.
Yes.
So how can you do these giant density fluctuations in, I don't know, elongated boxes?
Yes, you can do it.
In one direction?
You can do it. There is, I think, a paper by John Toner where he attempts to do this.
Okay.
What we typically do is, again, for simplicity reason, to use square boxes, which amounts basically to taking an average. But yes, but if you take very elongated boxes,
and
you
grow
expect,
in one direction.
if you do like this, or if you transversal or longitudinal, you find different scaling, yes. I don't know how precise are if there are precise numerical simulations, since, of course, John does the theory, and yes.
This is awesome, by the way. I'm trying to understand from the argument that you presented, if I measure the number fluctuations in some particular model that I'm working with, can I just use the number fluctuation measurement to estimate the change in compressibility that I should expect when activity is a given value or something like that? That is to say, I can change compressibility of the system by 10% if I enhance the number fluctuations to have an exponent or something.
Well, I mean, in principle, this is going to be the prefactor. So, I mean, never tried this, so I don't know how it may work in practice, but since this behavior is proportional to the compressibility, of course, the scaling law stays the same, but what is changing is the prefactor. So if you have, of course, fluctuate, I mean, the compressibility is going in equilibrium system to impact the relation between fluctuations and averages.
Right, but the prefactor is what is controlled by the giant number fluctuations. That's what you're saying.
No. The prefactor is always there. I mean, this is true for every system.
Okay.
If this is finite, you have that the square fluctuation are proportional to this. Okay, and then in equilibrium, this is the compressibility. Now, as you know much better than me, when you go outside of equilibrium system, all this kind of thermodynamic equivalence breaks down.
No,
so
but mechanically, it still has to be the compressibility.
Yeah, okay, of course. You can define mechanical quantities, you can define functional state, whatever. You don't have a free energy from which you can derive, but mechanically, yes, this is a mechanical definition of compressibility. Good idea. Let's do it. Very good idea. Okay. So far, I basically avoided, and we are to the end, to tell you what are these magic numbers. Now, the state of the thing is that it is very difficult to extract them from the theory. I will tell you about what has been done about these in the next two lectures. We had a very recent breakthrough, as I told you, which put forward the theory where you can compute this exponent. But until a few months ago, they were not known exactly, either in 2 or 3 dimension. Or okay, above 3 dimension, mean field theory applies and you can compute, but you have very few flocks living in 4 dimensions, so it's not very useful. What we did was to measure them numerically to a great accuracy. Okay, we did a few years ago. So we measure correlation function radially, transversally, to a great precision. And if you want to access the third dynamical exponent, you need to look at spatial correlation function. In particularly, you look at their form in Fourier space and from the width of the propagation peaks, which you get in the spatiotemporal picture, you will see this. You can measure the scaling of these things. And whoa, I wanted to show the table, okay. And basically, you can extract some kind of precise estimate, which then you can use to go back and check over quantities. Okay, these are numbers, don't worry for the moment. So the status that we have numerically. The interesting thing, which will be used later, is that there is an hyperscaling relation, which appears very clearly in the numerics, which is, okay, I try to just explain this. This looks a little bit odd, but this Greek Z exponent is a combination of the anisotropy and the roughness exponent. All of this part here, D minus 1 plus anisotropy, is just D, okay? Especially if there is no anisotropy. This is just telling you, okay, this is the space contribution, remember. When you move from real space to Fourier space, you get a factor D of D dimension. Now, if you do it with anisotropy, you subtract 1 for the longitudinal dimension and sum in its place the anisotropy exponent. Okay? But if it's 1, like it is going to be, at the end, this is just cancel out. So it's dimension plus this 2 times this roughness exponent. And this is the static part, if you want, of your correlation. And numerics tells you that this is exactly equal to the dynamical anisotropy, okay? And this is interesting since for this to be exact, of course, numerics cannot tell you how much is coincidental, but to be exact, it implies a kind of spatial structure in your hydrodynamic equations, okay? So it has, if you want, a consequence in driving you towards a correct treatment of the theory. So this is basically what emerges out of this. So we had these exponents, and okay, another consequence I don't have, I think, the time to go through today is that since you have very strong correlation, also, if you look at the displacement of a particle in time, so basically you have your flock, which is going this way, and you look at the particle here at time t, and then look at a little bit later, and you look at t plus tau, and you look by how much it moved transversally with respect to the direction of motion, okay? So, of course, the transversal movement is going to be zero average, so it's a kind of diffusion-like behavior. But if you look at the square displacement, you find that in certain situations, for instance, in 2 dimension, your behavior is super diffusive, okay? So you have seen Brownian motion, you have seen diffusion for 2 days now, and you get this relation that the mean square displacement was proportional to time, not equal, proportional to the diffusion constant. Now, here, as a consequence of this strong correlation between velocity at different points, it may be larger than 1. This is what is called super diffusion behavior, okay? And this is rather interesting since there are a lot of models in physics where you have super diffusive behavior, but typically are models which are explicitly devised to have super diffusion. Basically, you insert in the definition of a model a power law, okay? Typically, you have structure which has some kind of fractal behavior, or other kind of, you can get this kind of anomalous diffusion process when you look at scattering of light particles in crystal with scatterers which are power law distributed in sides. But you are putting by hand a power law, and you get out a power law, which is perfectly nice, it's interesting. Here, it's a little bit more interesting to me since we have not been putting explicitly by hand any power law. We just said we have a continuous symmetry breaking, then let's see what happens. So, okay, there is a calculation which I don't have the time to go through now, but who of you is familiar with the Kubo formula for diffusion? Yes, you? Okay. It's basically based on the idea of the Kubo formula. If you know, the Kubo formula for diffusion relates diffusion constant to the correlation function of the velocity, okay? To the integral of the correlation function of the velocity. Now, since if you have it's like the structure factor. If your correlation function for velocity decays fast enough, decays exponentially, it has not a power law behavior, this integral is going to be constant. If it decays very slowly, you get a diverging diffusion constant, which means that you are super diffusive. Maybe I can give you as an exercise for Thursday. Okay, so the result is basically that if you do the calculation and a certain condition are met, so this exponent can be larger than 1. And this happens in 2-dimensional flocking. It doesn't happen in 3-dimensional flockings, where fluctuations are slightly more suppressed. Okay. And that's it. And okay, I think it's time, and this is a good point to stop. Okay, so the main message is we have this kind of rather interesting phase. Of course, I'm much slower than what I would have liked, so tomorrow I'll still show you experiments and some other consequences, and let's try to do some hydrodynamics by the end of the week, sorry. Any questions?
I have a quick question here.
Yeah.
I think I got from one of your slides that the upper critical dimension for these systems is 4.
Yes, well, it was not written. We will see it if we manage to do hydrodynamics.
Okay. So that has not been proven, or is that a conjecture? Is that something that
No. This is very clear. If you as long as you believe that the hydrodynamic equation we are going to write at a certain point are correct,
Okay.
it's obvious. It's
Got
just, but the upper critical dimension is in most system is, well, not in all systems.
Okay,
right, in this system is easy
thanks.
to check. By the way, on dimensionality, if I may add one thing, sorry, it's a little bit, in general, well, birds may be an example of three-dimensional active matter, even if gravity is a special direction, and actually birds don't like so much to change altitude, so already is some kind of a special direction. Maybe fishes are, but okay, there is always gravity. In general, it's very difficult to have three-dimensional active matter for a number of reasons, especially if it's synthetic active matter. Since if it's synthetic active matter, like colloids, you need to inject energy in your system. And if you want to inject energy in your system, you need to arrive from an unexpected direction which doesn't break any symmetry. So this is very easy to do if you have two-dimensional systems, if you arrive vertically. If you have a three-dimensional system, it's much more difficult. For instance, if you have all these experiments with Janus particle which catalyze a chemical reaction, they keep going as long as you have a stationary amount of fuel, since you have a chemical reaction going on. Now, you need to give the reactant to the system to keep it going. And if you have a three-dimensional system, you can only give it from the boundary. And so you create gradients, and it's a mess. If you have a two-dimensional system, it's much easier. Okay. Yeah, but I'm not saying you cannot do, but I'm just saying that most of active matter ends up being done in 2D for this reason. I'm not saying it's impossible. Okay, sorry.
So you didn't mention the so-called violation of the Mermin-Wagner.
It was later. I'm slow, I'm sorry, and then, okay. Another thing we're going to talk about is the fact that now, and this is basically was the beginning of the story in '95. All of this scale-free behavior in equilibrium system turns out that these very strong correlations are so strong that destroy order in two-dimensional system. This is what happens in the XY model of ferromagnetism. Okay? And there is a celebrated theorem, Marmin-Wagner-Hohenberg theorem, which tells you whenever you break a continuous symmetry by local interactions in an equilibrium systems in 2 dimensions, there are a lot of little requirements, you cannot have global order on the asymptotic scale, which is what we call long-range order. Okay? You can have a very special kind of ordered system in 2 dimensions, which is called quasi-long-range ordered, which I will tell you later. But it's a theorem, so there is no way. Of course, what happens is that these little errors are not an equilibrium system, as I told you. So in principle, they do not have to obey Mermin-Wagner system. Now, of course, it's not even granted that they have to violate, they have to develop long-range order. So this was probably the main original motivation by which the hydrodynamic theory was developed. And it turns out that if you allow things to move in the direction where they point, you escape Mermin-Wagner theorem in 2 dimensions. Okay? This was explained by the popularization by John, who likes a lot these kind of things, like birds are birds are smarter than nerds. So basically, the idea is that if you have a lot of people who wants to find a common direction of motion and discuss about it without moving, they are doomed. They are not able to do it. If the people is mindless and start first walking, and then they try while they walk to walk in the same direction, you can do it. That was basically the distillation of the idea. Okay. Later.
More questions? I have one.
Yes.
So you showed the critical point of the equilibrium phase diagram, and then the critical point going to infinity.
Yes.
In the case of the flocking fluids. If you have both steric interactions that give rise to MIPS, which is somewhat similar to normal phase separation, and you have alignment between the particles, would the critical point be in the middle?
I believe that, well, two things. In general, I believe that if the alignment interaction are strong enough to change the symmetry, you're pushing the critical point to infinity. I mean, you cannot see it, you kill it in a sense. Since the entire intuitive idea of the critical point in liquid gas is you can go around, I mean, you have a transition line in the liquid gas thing, which ends at a critical point, which tells you, if I cross between gas and liquid here, I feel a jump in the density. But there is a trick I can do like this, and I don't feel any jump. I don't realize that I crossed the line. But if you have a change in symmetry, this argument doesn't hold anymore. You realize that you're changing your phase. And so there cannot be a point where your transition line ends, your discontinuous line ends. That's the idea. So if you have a change in symmetry, you don't have a critical point, I believe. If you don't have a change in symmetry, you can have it. I don't think it has even been measured with precision. I asked Julien Tailleur and Alex Solon, and they told me it's very, very complicated numerically.
For Vic-Check disks?
No,
for self-propelled disks?
For MIPS. For MIPS. Okay. I don't think there is, no, I can be as ever, someone can tell me last year they did, but it's very difficult to analyze numerically the critical properties of this MIPS point. I think someone claimed that it's related to easing in Italy, but I don't really believe that they did a very precise, I don't know what you... And on the other hand, another thing which it has to be reminded about MIPS, that pure MIPS, as we know, assumes the total lack of alignment interaction. For the reason I told you, there is always a little bit of alignment interactions, which, even if they don't provoke long-range ordering, they can promote local ordering. And this is some kind of perturbation on MIPS, and it may be one of the reasons for which it's very difficult to make experiments which reproduce quantitatively the MIPS theory, okay? There are a lot of issues in MIPS which you know better, like the arrest of coarsening and this kind of things, which probably, I think, came from this factor, but Aparna knows more. Okay.
Okay, so I am in trouble because I'm looking at this kind of stuff.
Good luck.
Yeah.
And how is it going?
I mean, I'm looking at the papers now, and I'm crossing the critical line, not there at the critical point itself, but at other parts.
Okay.
I mean,
away from the critical point, the critical line is fine.
yeah.
If you go near the critical point, you're inviting sorrow into your life.
Yeah.
That's
But
a
you know,
very good
the last
definition.
papers by Thomas Speck, yeah, no? Okay. They claim that indeed it could be he's in universality class, but it's not.
Okay, also Thomas is
Yeah,
claiming
Thomas
it,
Speck
okay.
as well.
I have
And
to-
Lee from, I forgot his first name, from Imperial College.
Okay.
I mean, he was certain that it was
So you know
easy,
more,
and then Thomas said, okay, it's probably not
you know
easy,
much
I don't
more
know.
than me on this subject, okay. So.
No, a little bit. More questions?
Is this large correlation size due to this kind of particles with alignment terms, or is due to nature of the system because this is active, for example?
No. It's due to the fact that you're breaking a continuous symmetry. So
sure.
it's due to alignment in the velocity.
Works for active baryon particles too?
Active baryon particles do, if you keep active baryon particle, like I showed you yesterday, with kind of alignment, they're going to do. And tomorrow I will show you a situation in which they do. And they have exactly the V-check phenomenology. But they have to align strongly enough to break the continuous symmetry. I had it somewhere, here. So if you do this, if you play this game, and you put a kind of alignment there, and this is very strong, so tau here is small, you get the same phenomenology. Or at least there is a corner of the phase diagram where repulsion doesn't jam your system, where you get the same phenomenology. Okay, so this is due to the spontaneous symmetry breaking. Now, the fact that you also move changes a few things. First of all, tells you that also the density now matters, and also the density is correlated over large distances. It tells you, as Pablo pointed out, that in 2 dimensions, you are non-equilibrium, so you can beat Mermin and Wagner. And it changes the value of the critical exponents. This is basically the three things which it does with respect to equilibrium. It's really a combination of the two things.
Because when we have motility-induced phase separation, we have large correlations in the dense phase, for example.
Yes.
And this is due to...
No, that's a different thing.
Phenomenal.
Okay. But note, you should be careful. You have large correlation, not, long-standing, sorry. You have strong correlation between the density field, not between the fluctuation of the density field.
I see. Yeah.
It's the same thing which happens in Ising. In Ising, if you go and measure correlation far away from the critical point in this double well regime, as I told you, everyone is more or less here in this bottom. So you will find that the spin itself are correlated. We are all going in the same direction. But it's the fluctuation. Here, the fluctuation gets basically decorrelated by the fact that they live in the bottom of the well. So everyone, when tries to steer away, feels this kind of potential, and this kills correlation between fluctuations, which, when you break a continuous symmetry, you have this continuous valley, and then there survives.
Okay, sorry, in the interest of time, let's thank again. Thank you very much, Francesco. And now we're going to have basically picture time. So it's group picture now. And coffee break and posters. Time is not too good, so we should be quick about discussions in the poster and so on. And then we come back at 11. Okay? Thank you.